get started. Welcome everyone. Good morning or good afternoon or good evening, depending on which part of the globe you are from. Thanks for joining today. We are here to have a CAT for Assurance webinar. And this is probably the 19th tool demo / webinar we are having in last 2 years or so. We'll talk about a little bit on the background of this CAT for Assurance initiative. And then we'll let the presenters today to present their tools or technologies. So the cat4assurance.org website, I think probably most of you have visited that website. Was created, and some of the activities which we undertook that started October 2020 by a large part of the hardware security community. A significant number of contributors to the hardware security community came together with the goal for having academic dissemination of tools, particularly the tools which we wanted to have as an open source tools. The hardware security benchmarks, metrics, some of the publications. So all of these materials we wanted to put in a web portal which can be accessed by the research community, by the practitioners from across the globe. So with that goal in mind, again, collectively, we reached out to the contributors, and we have been fortunate to have more than 80 contributors from across the globe who have uploaded their tools, benchmarks, or metrics in that web portal. Along with that, we also started the tool webinar demo, as well as some hardware security trainings. And we also wanted to have virtual panels on important topics in hardware security and trust. And we are very fortunate to have a significant interest and participation in these activities. As you can see here, we have done 18 tool demos webinars and 1 hardware security training so far, 5 virtual panels in last 18 months, and we had more than 1,500 attendees from different parts of the world. The website has been extremely popular. We have got about 10,000 unique visitors, unique users, and then more than 30,000 page views. Of course, every day we are getting a lot of new visitors and a lot of new page views. So the interest is there, and we really appreciate the contribution by the community. If you would like to help with this effort, we will strongly encourage that you submit your contributions to the website. If you're interested to do webinar, please let us know. If you're interested to take part in the panels, also let us know. We are fortunate to have a number of sponsors for this event. IEEE CEDA is the technical sponsor. Warren B. Names Institute for the Connected World at University of Florida. IEEE HSTTC, that's the Hardware Security and Trust Technical Committee in IEEE under CEDA. And then several companies, Mercury, Huntington Ingalls, and Northrop Grumman, they came out as sponsored for these events, and the organizing team primarily consists of these 4 members. As you can see here, myself, Dr. Ganku, Dr. Sung Ho, and Dr. Ye Jin. So with that, I want to quickly talk about the activities which we are undertaking. You see there's a large number of activities. The one important point I would like to highlight here is that for pretty much all these tools, webinars, virtual panels we are having, we have recorded them. We have got permission to distribute them in public, and they are all available in IEEE CEDA website. So if you are interested to look at them, you can do that. If you have missed some of them, feel free to look at the recording, and also feel free to circulate these events to your colleagues or to your peers. Today's event would have 2 different webinars. So before I go into introducing the speakers today, let me quickly talk about 2 things. Number 1 is that this event is going to be recorded. So I hope you give permission to record this event. If there's any issue, please let us know. Number 2 is that the Q&A or question and answer session would be through the Zoom portal. If you have any question, please put it in the Q&A tab. Click on that tab and write down your question. You do not have to wait until the presentation is complete. You can actually submit your question anytime during the presentation. So with that, let me introduce these two speakers who would be giving the demos and webinars today. The first one is called DANA, Universal Data Flow Analysis for Gate Level Netlist Reverse Engineering. And it will be presented by Nils Albartus from Ruhr University, Bochum in Germany. He is a PhD student and researcher at the chair of embedded security at Ruhr University, Bochum. He has done Master of Science in IT Security. At the same university, he has research interests which include reverse engineering of hardware Trojans, and hardware obfuscation. These two individuals, both of them are very young, but they're rising stars. They have already made significant contributions in the hardware security domain, and we expect from them to have more contributions in this area. Then the next speaker is Jonathan Cruz from University of Florida. He'll be talking about hardware Trojan benchmarks from chips to PCBs. This is a collection of benchmarks which he has created in collaboration with some other researchers at University of Florida, and they are publicly available for your evaluation. Jonathan is a doctoral student and is a researcher at Electrical and Computer Engineering Department at University of Florida. His research interests include hardware Trojans, IP protection, and system on chip security. With that brief introduction, I would like to hand over to Nils to give the first webinar today, and that will be followed by the webinar by Jonathan Cruz. Again, welcome.
Thank you. Nils. Thank you for the nice introduction. Yeah, I will take right over if I can share my screen. Yeah. Perfect. So if you can see everything. All right. Yeah. So as I've already been introduced, I'm Nils. I'm from the Ruhr University in Bochum. Or more precise, we've now kind of switched to the Max Planck Institute. There's a new one that has been founded like 2 years ago, which is dedicated to do research in just security and privacy. And with that, in Bochum, we have like over 200 researchers, so including postdoc, PhD students, professors, that are focused on various topics in cybersecurity here in Bochum, from ground research and math to hardware and software security, and also human factors. So today I want to talk about 3 things. First, I want to give a short intro to Hdl. I want to give, as promised, the short demo of DANA. And for the last part, I want to talk about new features that have been coming up that we've been developing in Hdl, which is the dynamic analysis. And after each one of these 3 things, I'm going to give like a short demo to actually show you how this works and how Hdl and how these things actually look like. So I want to start with like some intro slides to our research in general, to the research of hardware reverse engineering. And I actually want to start with the entire process, and we're going to skip right quickly through it, but it's important to have as a background. So there are kind of like 2 ways to get to the netlist. So one is starting with ASICs, where you have to like first encapsulate the chip and do like delayering, imaging. This all requires very expensive and fancy equipment. And once you have all these images from the chip, you need to process them, and then eventually you will retrieve your netlist and start your netlist analysis. But there's also like another way to get your netlist, which is for FPGAs, starting with the bitstream extraction, and can extract that from like some non-volatile memory or somewhere it might be stored in the firmware, because FPGAs are consist of non-volatile memory, and they have to be flashed once they start up every time. So the bitstream often has to be stored like externally, and you can extract it. And once you've extracted the bitstream, you convert it to a netlist, since all these zeros and ones in your bitstream are basically just another representation of what the netlist looks like. And there are a bunch of projects out there that are open source that aim to document these bit streams, and they've like made really great progress. So the database that they have is pretty good. So actually doing the second step has become more feasible in the in the last couple of years. And it's actually like a really nice entry point to Netlist reverse engineering, since it doesn't require all these fancy and expensive equipment as it does for ASICs. So once you reach the Netlist, so we have often talked to people and, they didn't have an idea what Netlist reverse engineering looked like. And they thought, yeah, aren't there like these blocks? And isn't it like super easy to do this? Well, actually isn't, because this is not how it looks like. It looks more like this. So this is like what we used to call, or what we like to call, the sea of gates. So you see like a bunch of thousands, 100,000, millions of gates and their connections, and it's kind of hard to actually work with it and figure out what is going on. One thing that helped is the analogy that we have been using, or the scientific community has been using for the last couple of years. That is that you can use, or you can interpret the netlist as a graph. So every gate that you see there, you can like see as a vertex, and all the nets, so all the wires in between the gates, you can see as edges. Yeah? So going from the digital netlist, you can actually go to a directed graph and make use of algorithms from graph theory to actually analyze the netlist and go on with your understanding. So what netlist reverse engineering kind of looks like for us is you can like divide that in 3 phases. So phase 1 is the netlist recovery, so actually getting the netlist. Then in phase 2, this is what we like to call the netlist preprocessing. So you're kind of trying to identify some building blocks, so for example, adders, counters, whatever you have, registers, to have like a more high-level view on the system. And then in phase 3, this will help you to actually make sense of what is going on in the hardware design at a system level. And these last 2 things, this is where HEL comes into play, and those things can be done in HEL. And I'm going to show you what HEL looks like in a couple of seconds. So when we started HEL, which is, I think, about 10 years ago, so it wasn't even me who started it, it was like the PhD generation that came before me. We were kind of jealous of what was going on in the software reverse engineering group, because they had like these great tools that allows them to reverse engineer the binary, which is, if you want, kind of pendant to the netlist for the software people. And they had like these great tools like Hdl and Ada Pro which allowed them to reverse engineer the binary, so that you can implement like some algorithms on there, have some plugins and whatnot that actually help you make sense of what was going on. And back then we wanted to do the same, and this is how we started HEL. And HEL has been open sourced by now. It's on GitHub, everyone can download it, everyone can contribute to it. And it's a very modular netlist reverse engineering framework, which is written in C++, but some people don't like C++, so don't worry. There's also like a Python interface, which allows you to use most or almost every function that HEL offers also in Python. So we have wrapped that for very easy prototyping and very easy use. All right, so just a quick outline of what HEL looks like internally, and this graphic is a little bit outdated. I didn't have time to make a newer one, but still, like most of the things you can see here are still true. So what we have is we have the graphical user interface in HEL, we have the Python shell, and we have a plugin manager that is able to load all kinds of plugins. I'm going to show you some later. So for example, a plugin that tries to identify FSMs, you have a simulator available, Boolean functions, all kinds of things that assist you in understanding the netlist. And the netlist, when you open it in HEL, it's being parsed by our HDL parser. So you can currently input netlist in the Verilog or VHDL format. You can write your own parsers to support more formats. And internally, the netlist is converted to a graph. You can operate on the graph. You can modify the graph if you want. You can annotate things, and it's all like saved in some project files. And even if you want, you can like manipulate things. So we also have Hdl Writers available, which allows you to, for example, in the cases of FPGA netlists, insert a Trojan or whatnot into the netlist and then write out a modified netlist, which you can then generate a bitstream from and have like a modified bitstream in the end. So all of this can be done in Hell, and all of the plugins that we have available output like some reports that will assist you during the reverse engineering process. The graphical user interface is probably the most exciting thing that is really helpful for us, for the things we have been reverse engineering to actually make sense of the stuff that we want to see. So as a summary, kind of what Hell can do for you. Hell is a framework that allows you to parse the netlist and gate libraries. So Hell is kind of technology independent. So as long as you have the gate library that belongs to your netlist, you can use Hell for your analysis. Our core features provide functions to interact with the netlist, and I'm going to show you how that works in a couple of seconds. We have support for Boolean functions, which include SMT and TUT solver. We have support for simulation and also a plugin system which allows you to write your own plugins to assist you in the reverse engineering process. But what Hell is, of course, not. It's not a one-click solution, so you cannot input your netlist and then have everything wonderfully modularized or figured out everything automatically. So this is not what Hell is for. I mean, that would be the dream, and we are working towards that in 20 years or whatever. But right now, Hell just provides the basic functionality to analyze the netlist, and you can use it to do your analysis on. So I'm going to give you a live demo of what it looks like. This is our welcome screen that you can see once you start Hell. We're gonna, as you see, I've prepared like 3 example projects that we're gonna go through in the webinar today. So let's start with the first one, just a simple ALU. It's a rather small netlist. So if you can see here, you can see the top module. You can see all the inputs and the outputs that go into the netlist. So this one has like couple of outputs, 18 inputs and 8 outputs. In total, our netlist has 45 gates. This is an Fpga netlist. I can look inside it. If I double click it, then I get this nice view with the graph and all the gates that are inside. So here, for example, you can actually see that it's an Fpga netlist because it features LUTs. I can click on that gate. I will get some more information. I can see the inputs and outputs to it, the nets that are connected to it. Hell also directly gives me the Boolean function that the gate is implementing. So the actual function that it's implementing on the chip, that's derived from the configuration string that is saved with the LUT. You can actually view also the truth table here. And if there's like some other data available, for example, the position that is placed on the FPGA, it will show up here. So here's another element, so the carry element, which is like a bunch more outputs. So you can see the Boolean function for all of these outputs. So one thing that we usually like to do is we like to create modules. So to like basically divide and conquer our bigger problem here. And the way how that works is, for example, you figured out that these couple of gates right here actually have something in common and form a module, and you want this to be in a module in Hell as well. So you can create this nice little module here that will show up here and also on the module widget that we have right here. Double click it, and I'm going inside the module where I can see all the gates. I can create another module. So I can create a submodule here. Will then be nested inside of my parent module. So as you can see, I have now a submodule in my my module. And I can also unfold these again so that these show up here again. I can fold this. So this is pretty nice. One thing that we like to do very often is we make use of our cone view. So you can, like with a right click on one gate, you can isolate the gate in a new view. And then this thing opens up here. And what you can now do is you can basically click on these input ports, and with the arrow keys on your keyboard, you can add the gates that are in front or after the gates. So basically you can like traverse the graph in a limited view where you can like click all the gates that are relevant for you right now for your analysis together, so that you're not overwhelmed by the entirety of gates and analyze single parts of the netlist. So you can like go farther, on till the very end, till you reach the inputs. Basically, you can also use some functions. So, for example, you have the option to add like the predecessors of one gate to your view. So basically, then all these gates are added in front of it. You can move gates around if you don't like how they are aligned here. You can basically move them anywhere you want. Yeah. So this is kind of it for the graph view. And one of the most exciting features that we have is probably the Python editor, where you can interact with your netlist that you've opened on the left and use some functions that we are providing in the back end of Hdl that are written in C++ that we have wrapped and put into Python, that you can call directly here in the graphical user interface. So one thing that I've been doing here is just wanted to show you a quick example. We're not going to go through it in detail, but this is basically, since the small netlist that I've just opened up, it's an ALU, yeah, with, I guess, these 8 input bits for A and B and 8 output bits, can have like multiple functions. So if the opcode is, for example, 0, 0, the ALU here might behave as an adder. And what I wanted to show you here is that with the help of our Boolean functions, you can actually verify, kind of formally verify, that this is behaving as an adder under certain conditions. So what we want to do here is we want to generate the Boolean functions for all the output gates, which means that, for example, this is one of the outputs here for the output nets. I want to get the Boolean function for that net that is depending on all the other gates in front of it. So I just want one function for that. And I want this for all of my 8 inputs, right? 8 outputs right here. That's what I've been doing here in these lines. So there's a function called getSubgraph function that gives me the Boolean function for this net as a dependency on all these input nets. And you can then, in the end, basically have your model you want to compare it against to. So I'm building here an adder, an SMT. So I'm basically saying that I have 2 variables, yeah, A and B, both are 8-bit long. I want to add them, and then I want to compare it to the Boolean functions that I've just been generating here. And I want to check if under the condition that the opcode is both 0, if my ALU behaves as an adder here, I can execute this little script. And I see all these Boolean functions are kind of printed here. And then the SMT server says, yep, my ALU behaves as an adder since the constraint is unsatisfied. Okay, just a small example of what you can do and how things work. This example is also in our example folder. We have been reworking this feature in our new Hdl version 4.0, which is currently still in a development branch, but we want to merge that to the master very soon. So this will be hopefully coming out very soon, and yeah, for everyone to use. Okay, so let's go back to the presentation really quick. Yeah, I can. Okay, so I just want to talk about Dana a little bit, and I want to show you how Dana is integrated into Hdl. I will do a short recap. The full presentation is online, so I'm not going to go through all the technical details, but what Dana tries to do, it tries to structure the sea of gates that you have here by recovering high-level registers. And this was our publication at CHEST 2020, so about like 2 years ago. And basically how Dana works is 3 easy steps. We kind of ignore all combinational logic, so kind of remove it, and we just care about the connections between every single flip-flop with one another. So afterwards, once we kind of removed all combinational logic, we apply some small and simple metrics that analyze, for example, the control of the flip-flops or the input and output behavior, how that compares to another flip-flop. So we have like a bunch of small metrics that try to identify higher level registers and then creates register out of it. So this is in a very short summary how Dana works by combining a bunch of different metrics. And what Dana made like so special back then was that we kind of wanted the data to decide by itself what the final output looks like, meaning that we have like several iterations. So we create like one register and then we basically input that again into Dana, and then Dana tries to identify other registers depending on what the current state looks like. And once all the registers have been identified and nothing changes anymore, Dana is basically done and has like a final register grouping. This is of course not perfect. It's a heuristic method, so don't expect like 100% perfect results. We have been using this, however, on a real world design that we've been reverse engineering for a couple of months now, and we were actually quite surprised how well it works. So yeah, feel free to use it. I'm going to show you what you can. So let's open up Hell again. And I'm going to open the netlist that we have in the paper as well for the Trojan case study that we did. And as you can see, this is already much bigger. So this is the top module for the netlist right here. Click on it. See here that it has 10,000 gates in it. So it's quite bigger than the netlist I just opened. This is synthesized with the non-gate library. So you can see, yeah, basically a bunch of Asic gates in there and no more LUTs. Yeah, so if I were to open this, our layout would take some while because it's 10,000 gates almost. So I'm not gonna wait for that. I'm just gonna show you how to use Dana. So we have a new feature here on top that is called plugins, and you can start the data flow plugin right here, which basically allows you to set some parameters, the parameters you want to have before Dana does its thing. So Dana wants me to set the following. So this is an optional parameter. We had like 2 different modes in Dana, where you can, if you want, give Dana like some hints of what you're expecting. I'm going to tell Dana that I'm expecting registers of the size 128, which means that I'm expecting my registers to have 128 flip-flops inside of them. Since the netlist that I just opened is an AS128, which means that we have a 128-bit key and a 128-bit round state or plain text input. So this is kind of the register size that I'm expecting. This is what we call in the paper the bad group size. So Dana is good at recovering the data flow, but it's not very good at recovering like state machines, so state registers. So this is what we call like the bad group size. So we are not very good at just like recovering very small registers, but bigger registers, since we analyze the data flow in the netlist. But this can be like set to a bunch of different values here, so you can play around with that. And then you have a bunch of options here in the end for Dana, what you want to do. I'm going to activate that one. That will generate me a nice little graph of the netlist that shows how the data actually flows inside. Then I can basically start it. So this is running for a couple of seconds, and we can watch what's going on the terminal. So Dana already finished and it generated this dot graph for us, which is depicting the data flow. We're going to get to that in one second. I want to show you first what this looks like in Hell. I can use it. So Dana created a bunch of registers here. So if I click on one, I go to this general tab down here, I can see how many gates are inside this register or module that has been created by Dana. So this is exactly 128 bits. Can again now isolate that into a separate view. This is now my module. I can double click it and I can see, wow, there are like 128 small flip-flops inside. So it's a data flip-flop that only has like this data port and the control, the clock port. Yeah, there's 128 of them in here. Fold that again. Okay. So I can also use the arrow keys again to explore this a little bit. So there's a max gate in front of it here, some XOR, and now I've reached another flip-flop, which is marked in orange, which means that it's another register here. So I can fold this if I want, and it's another 128-bit register, and they are connected via a bunch of gates on the way. So this is kind of the data path, and those are the flip-flops or the high-level registers that Dana has recovered. And this is the data flow graph. And as I've promised, Dana is not necessarily very good at recovering the state machine. So these bunch of 1-bit, 3-bit registers that you can see here are probably forming the control flow. Yeah, and this is most likely some kind of FSM that's controlling how the AES is working inside. This is like a round-based implementation, so we need like a counter that's keeping track in which round we are. And this is probably implemented in these registers here to actually control the data flow in here. And then we have a bunch of 128-bit registers that you can see here that have like a bunch of different functionality. So maybe let's just look at that one here. That is the one that is probably the output register, since it has a bunch of inputs from a couple of data registers that you can see here, but there's no arrow going out of it. So this is probably where the final result will be stored, and then outputted to the output pins. And these are the input registers, and they have no input here from another register, only from outside, basically, from the outside the top module. So one is probably for saving the plain text, and one is probably storing the key. You can actually confirm this. So let's have a look. So this is the register with ID 0. And we can see Dana register 0 here. So let's isolate that in a new view. 128-bit looks good. And if I click on that one, it will give me the name of this net, and which is actually like the ciphertext. So if I go back to my top module, this is probably the output bit. Yeah, you can see it here. It's just been marked. That goes out of the AES one from that specific flip-flop. And I could do the same now for example, for this one. And this is the one with ID 1. If I click on the input here, yep, I can see this is the key. And this is basically what Dana does for you. It will generate these nice graphs. It will generate these nice registers here in your netlist, so that you have like a more structured view of things, and makes life or your analysis a little bit easier. Okay. Let me go back to my presentation really quick. Oops. So I wanted to talk about something we have been working on in our group for an upcoming publication. It is still under submission, but I wanted to show you how this new feature in Hdl works, since I think it's actually pretty cool and it might be useful for other people. So we have been working on simulation-based analysis for some time now, which means that this would allow you to observe the behavior of the circuit over time. And the big advantage is that you don't have to focus on your control paths necessarily, because if you have like the correct inputs applied to your circuit that you're kind of analyzing dynamically, the control behaves like you want it to, and you can like focus on analyzing the data paths, because you can see how the bits flow through the data path, which might help you understand what is going on. And we allow in Hdl for partial simulation. So you can, for example, only simulate like pre-identified modules, which is much faster, or you can simulate your entire netlist, which of course might be slower since your netlist has like a couple of gates, thousands of gates in that. So this can like take hours to days, depending on how big your netlist is. We've been calling this virtual probing because it kind of allows you to access each signal at any given time and observe how it behaves. And we have been working on a new plugin here, which is the Netlist Simulation Controller, which can be controlled by the GUI, our Python interface, or also via C++ plugins. And in the backend, you can attach or you can write support for any kind of simulator. So this can be industry simulators in, I don't know, your Vivado simulator or Model Sim that you plug in there, or open source simulators like Verilator. So you can use those tools to actually simulate your netlist and then read back the result of the simulation and apply it into Hdl to support your analysis. And we've been doing this for some time now. So what this looks like is that you basically create in your Python instance that you saw on the right in Hdl. You get the Netlist simulator plugin, get the simulator controller, and then you can select an engine that you want to simulate with. Right now we only support Verilator since it's open source and free and available for everyone. And then you can write basically a test bench like you usually would when you're designing your hardware cores. So you basically set a clock period, which you can add to the simulator, and then you just basically write the test bench like you usually would by setting different signals, for example, the reset signal, to different values over time, and then tell Hdl to simulate for a specific amount of clock cycles or picoseconds, whatever you have. And in the end, once all your simulation or your test bench is kind of done, you can tell Hdl to run your simulation. If necessary, you can like provide models of the gates that are inside. So for example, if you have very complex models like a DSP or a VRAM, you can tell Hdl where you can like find the Verilog description of them, and it will then apply them to the simulation as well. Because for very simple gates like AND, XOR, or LUTs, we can generate these models for the simulation engine, but for the very complex ones, we can't, since this is far too complicated, and they all have like they're all kind of different. So the results can then immediately be viewed in our waveform viewer or in a standard waveform viewer, or also directly in Hdl, which is much nicer since the values are directly assigned to the nets and you have a direct visualization of the results in the graphical user interface. And we did this for a real-world design, and this is an upcoming publication from us. So we basically designed a custom PCB that is able to intercept the signals that are coming in and out of the device. So this is the custom PCB that we designed here in blue. And we took out the FPGA that was running on there. and inserted our interceptor PCB between the FPGA and the PCB. And this allowed us to observe the inputs that are going into the FPGA during runtime. So we actually had the correct inputs, like the real world inputs of the design that are applied there. And we recorded all of them with the help of a logic analyzer. And in the end, we applied them in simulation. And if you apply the real inputs, the real world inputs to your netlist in simulation, this means that everything propagates through your design, and you can actually, if you even record this for a couple of seconds, you can basically in hell then click on second 0.5 or whatever and see what value each net has at that given time, which has been great for us to understand what has been going on. I have a couple of more slides that would have shown how that looks like. I'm going to skip over them since I'm running out of time. But this is kind of what it looks like after it has been inserted. Took a lot of tries, and we destroyed actually several devices, but in the end it worked very nice and delivered very nice results. Okay, this is the video that I wanted to show. So on the right here, you see our waveform viewer. This is of course not the simulation from the real world device we have been analyzing. It's like a toy cipher netlist. So this is the standard waveforms you're probably used to when you're designing your hardware IP core. And here is the graph view from hell again. And every net is kind of colored right now. If it's colored in blue, it means that it's 0. And if it's colored in 1, it means that at that given time, go a little couple of seconds back, where the position of the cursor is right here, is 1. Yeah, so depending on where we are right now in the simulation, the nets are kind of changing throughout time. And this is especially nice if you have like all this basic blocks, so headers and counters already available, because you can actually see what real world data is flowing through the design and how this behaves in the netlist. Yeah, and this is a feature we have been designing on for hell version 4.0, which we are about to release very soon. Okay, thank you for your attention. That's it from my side, and I'm happy to answer any questions you might have.
Hey, thank you, Nils. That's an excellent presentation. Greatly appreciate all the details you have provided. I believe the audience also share similar appreciation for this. So we are running a bit late, but we should be able to take 1 or 2 questions. If you have questions, why don't you write in the Q&A tab? Just click on that tab and write your question. I know the Dana tool is already available in the CAD for Assurance website, and several research groups have been already using that tool. So also, again, that's great. There's a quick question on that. How does logic optimization such as ABC impact the reverse engineering?
Yeah, I mean, it of course makes it kind of harder, right? Because everything is much more optimized. Especially identifying modules is kind of very hard because these tools are very good at destroying these borders of the modules. Yeah, so everything is kind of merged into that big flattened netlist. So these things make it harder actually for the Boolean functions to optimize them as well and to have like an easier form, easier representation. We have been using ABC as well in hell to optimize our Boolean functions. But of course, the tools are always getting better, which makes it harder to reverse engineer the netlists that are coming out of them.
Okay, thank you. Any other quick question? Okay, calling once, twice. Okay, so let's thank Nils one more time. We have another, there is another question. So let's quickly answer that and then we'll move to the next presentation by Jonathan. So I'm not reading that question. Can you read and answer?
Yeah. Okay, so the question is regarding the real world application that I've shown in the end with our PCB connected logical analyzer. And so, of course, this could have been a problem if the operation was timing critical, but the FPGA was luckily running at a very low clock frequency. So the way we did it was we recorded the input signals and even the clock. So we were able to record the clock as it were running as well. So we applied all of that, we recorded all of that and then applied it into simulation. And it worked out pretty good. We were able to compare the recorded outputs. So with the logic analyzer, we also recorded the outputs to the ones that we were able to simulate, and they matched. So our simulation matched with the real world output. So these things, this can work. And I think the FPGA was running at I think it was less than 50 megahertz, maybe like 25 or something. So this was not that high. And of course, this doesn't work if this is like super timing critical. But for our device, that worked out great.
Okay, that's wonderful. So we need to move on. And thank you, Nils, one more time. So again, the recording would be available online in the IEEE CETA websites. If you want to follow up, feel free to follow up with Nils for future questions on his presentation. So we need to move on to the next one, and that will be given by Jonathan Cruz from University of Florida on Trojan benchmarking. Jonathan, are you ready to share your screen and proceed?
Yes.
Okay, go ahead.
Let me go ahead. So can everyone see my presentation slides?
Yes, it's visible.
Okay. So yeah, thank you everybody. So today I will be presenting on hardware Trojan benchmarks from chips to PCB. This is done at our group at the University of Florida and several other collaborators. So I'm just going to quickly give a brief overview of the threat and then jump right into the benchmarks. So as we all know that nowadays we have a horizontal business model. So we have a design house now needing to interact with several potentially untrusted parties. Now, a particular threat
Hey, John.
Yeah.
For some reason, some part of the screen was blocked by some black square.
Which part? Is it the top?
The top and the right bottom.
Oh, I don't know why.
Oh, maybe it's just me. Not sure.
No, it looks blocked for me too. So yeah, there's another box that came in. Maybe when you're clicking on that screen, that's why the block is. Can you click on that region?
So sometimes it's like the Zoom chat window or something that is on top
Zoom chat. So let me stop sharing quickly, and then let's see. Is it better?
Still have those boxes.
I am unsure.
More boxes are coming.
Okay, yeah. I mean, on my end, I have this top bar, and I'm not sure there's no minimize.
Can you go down to the bottom right?
Bottom right. I mean, for me, it's just my
click
slides.
on that. Click on that now. Click on
Yeah.
that and go up a little bit. Go up a little bit and click. Click the mouse. Let's see if that goes away. No, it doesn't. Okay, so why don't you continue?
Okay, yeah, sorry about that. So I'll try and see if I can talk around it. So yeah, so this threat of hardware Trojans is particularly prevalent, and it's significant in the fact that it can occur at every single one of these stages where a potentially untrusted party is interacting with the trusted design house. And then another thing with Trojans is that they have the effect of potentially perturbing the three main pillars of security for a design, namely confidentiality, integrity, and availability. So hardware Trojans are deliberate malicious alterations, and they cause two main effects, being denial of service or leaking critical information like key to a cryptographic circuit. And in general, they have a trigger circuit and a payload circuit. Now, depending on the level of abstraction for which the Trojan inserted, they will be occurring in or implemented in different ways. So this first image here in the top left we have is a combinational Trojan in an Asic gate level netlist. To the right, hopefully the box doesn't occlude it, but we have what would be a PCB Trojan where we have these microcontrollers on a PCB, and then we have added a malicious IC to instantiate a PCB Trojan. And then on the bottom, we have would be a Trojan in the Fpga netlist. Now, the primitives are different for FPGAs. They use the lookup tables or LUTs. And here you can essentially hide both the payload and trigger circuit in what would be one primitive structure. But what they have in common is that Trojans should be, stealthy Trojans should be difficult to activate to minimize the likelihood of detection during traditional verification and validation. And they should also have minimal footprint in area, power, and delay. And again, to avoid detection. So this is where we have these automated Trojan benchmarking frameworks developed by our group. So we have several tools across several different levels of abstraction for developing and inserting Trojans into any design. So two primary features are that we ensure that every triggered Trojan can be triggered and that every payload has an observable malicious effect. And then we have for three different levels of abstraction. For gate level, we have the first TRID-ASIC, and then from there we built off of that to go across two levels of abstraction, which are for TRID PCB for printed circuit boards and TRID DS for FPGA, which is our newest work, which is still under review, but the preprint is available. So I just wanted to highlight a couple things about automated Trojan benchmarking and the benefits of it. One is that we can quickly analyze the Trojan attack space for your design. I don't have to rely on hoping that somebody uploads a benchmark on CAD for Assurance that has my design with Trojans in it. I can go ahead and insert Trojans directly onto my design under analysis, which is very useful. It allows for unbiased benchmark generation. Again, if we have static benchmarks, the problem with that, it's good for comparing different techniques, but then what ends up happening is developers might start to tune their techniques to detect these Trojans only, and given that they're not entirely representative of the entire Trojan space, which is generally very large, this could be problematic. So we can kind of mitigate that by quickly exploring and going ahead and generating thousands and thousands of different Trojans, distinct Trojans for different threat models and the like for evaluation. This can also be used for design for trust in a closed loop solution. If you have a Trojan detection technique and you want to have a feedback loop so you can insert Trojans, see if they get detected, or see if I prevent insertion and continue this feedback loop until you get satisfactory results. And then as we see this surge of machine learning based, graph neural network based trust verification, we need data, we need large amount of data. So this kind of a framework can be used to generate this sort of robust data for machine learning. So now I'm going to go into the three tools. I'm going to give a brief overview of what's available on the benchmarks, and then we'll get a video demo. So the first set is the Asic benchmarks, which are generated by TRID-ASIC. So we currently have over 2,800 Trojans across 16 different designs. They are primarily ISCAS 85 and ISCAS 89 benchmarks. So they are in the format, so the link is there for you to access them. They're already rarely available. And then the format is a Verilog netlist. We have two libraries. The first iteration, we used a Lida library. However, there's some copyright issues exerted by Synopsys. So to avoid any of that, we kind of moved on to Skywater open source. So that library we provide with those types of Trojan benchmarks. And then in particular, the Trojans that we offer are triggered functional denial of service, both combinational sequential, and always on leakage Trojans, which are combinational and sequential. So a bit about ASIC level structures. So this is how several generic structures of ASIC level Trojans can exist. On the far left, we have a combinational Trojan that purely consists of combinational gates. And then we have, in the middle two, we have sequential Trojans. It can be a very simple counter or some sort of FSM that once it achieves its particular transitions or achieves a specific count value, it'll activate. And then finally here we have this moles Trojan proposed by Lin et al. That essentially leaks an asset through a side channel. So we use these as our base structures for our Trojan. So now I'm going to show a video of essentially what's available online. So let's go ahead and get that started. So here I just took some of them. So we have denial of service and leakage. So first we'll look at the denial of service. So here's essentially what's available. We have the directory partitioned into the combinational and sequential, and then we provide the original benchmarks without the Trojans. We also provide the library file. So this has the synopsis, DB file, the .lib file, everything you should need to go ahead and get this running. Now we have a README which essentially gives you an overview of what we offer, the number of Trojans, the type of Trojans, how many, so the number of trigger inputs, whether it's a combinational or a sequential, and then we have this rare signal threshold. So that's what we use to essentially determine whether or not, or a signal can be used as a trigger. So those are the thresholds that we provide there. And then now we'll go ahead and dive deep into what's, in some of the benchmarks. So we'll go ahead and look at, so here, each benchmark comes with the corresponding log file and then the Trojan inserted netlist. So we'll go ahead and we will look at the log file of one of the denial of service combinational. So we'll go to the top. So here we come with the common disclaimer, this is for academic use only. And then we give, for each of the Trojans, we give statistics, the type, the effect, what signal it's altering, what are the activation condition, what are the expected values for the signal, and then the Trojan body. And then so this exact Trojan body will be in the corresponding netlist that is also provided. So again, we have this disclaimer, and then it'll be all the way at the bottom, the Trojan that we saw previous. Now, to get a bunch of structural diversity, we implement this soft template-based approach here. So we define the Trojan behaviorally, and then we constrict the synthesis tool to use different varying level of gates to get functionally equivalent but structurally diverse Trojans. So to show that, we'll just quickly look at another log file for one of the Trojans just to highlight that, yeah, we get, even though it's completely different Trojan, different structure and anything, so we can get a robust data set. Now we'll look at the sequential. So there's a similar structure, every log and accompanying the Trojan inserted netlist. So we'll go ahead and look at that log file. And then here, it's a randomly generated FSM with the following transitions that have to occur. And then when it happens, since it's denial of service, it will perturb a signal. And then here's the structure. And then in addition to a random FSM, we also have counter-based. So we'll go ahead and look at that. So that's just, in this case, it's a 2-bit counter. So once it reaches its maximum value, it'll go ahead and trigger its payload. So with that, that's for the denial of service. And then we'll just take a quick look at the leakage Trojans. So now, again, we have the same structure. And the README here says that we have 20 always-on benchmarks, 10 are ring oscillator, and 10 are this moles based by Lin et al. So here we're just going to show you a quick what the ring oscillator based one looks like. So we'll go ahead and just open up the log file. And we'll show that, okay, its combinational effect now instead leaks this particular signal. This signal is randomly selected. And then in this case, it seems to be a 27-stage RO. So the number of ROs varies among the combinational always-on leakage. So now we'll take a look at the moles Trojan. So here, we randomize the size of the LFSR and the seed as well as the number of signals leaked. So in this case, we have a 21-bit NLFSR with the corresponding seed, the signals that are leaked, and then here is then again the Trojan body. The moles Trojans are rather large, so that's why we see all this gates. And then again, just for showing the structural diversity, we see now this case it's a 17-bit NLFSR. So now I believe that this concludes this portion. So now we'll go ahead and jump to PCB. So PCB benchmarks are available. So these we have 150. So this was primarily done by one of our other researchers, Aritra Bhattacharya. So here we have 150 Trojan inserted PCB across 10 open source designs. Here we use KiCad Netlists because they are open source. We provide all the corresponding libraries that are available and required. So, and then the types of Trojans that we offer here at the PCB are triggered denial of service and triggered leakage specifically. And then you can refer to the paper to get more details, but we have two general structure and components for the Trojans. We have discrete component based and we have IC based. So discrete component is, your resistors, capacitors, transistors, and IC based is we have actual, malicious chips that will carry out some malicious effect. So we have some, AND gates or chips, stuff like that. And interestingly, we also have for similar to the A2 Trojan for capacitor-based triggers. So this is almost like a sequential Trojan at the PCB level. So now again, I'll just go through the structure of what's available online. So this is readily available on GitHub, but there's a link through the CAD for Assurance. So here's just the generic README and some stuff about citations and what information you need to get going with our benchmarks. And then, so this is just a subset that I took. There's 150. So here we'll just look at what the general structure is for each of the benchmarks. So each Trojan file that is generated is accompanied with several files along with it. So the first one we have is, we'll look at the .NET file, which is the actual KiCad netlist with the Trojan. And then here it's, in the generic KiCad format, we have stuff about lib, your components, definitions, stuff like that, connections, and so on. So in addition to this, we provide report files. So here the report file will give you information about the Trojan itself, what signals are used to trigger the Trojan, what the effect is, and then we use SPICE simulation to generate and select the triggers, and we identify which simulation values are least likely occurring, and as we use as triggers. And then this distribution file essentially shows what's the distribution of passive components. So the first row is resistors, the second one is for the capacitors. So in this case, this design didn't have any capacitors available. And then finally, we have these .dot files. So this is just a graphical representation that you can use to view the design with the Trojan, or then just the Trojan structures themselves. So that's it for the PCB. So this is all available online. Okay, so then we'll go to the most recent effort, which is for Fpga benchmarks generated by TritDS. So here we have over 1,300 Trojan inserted designs in pre-place and route Fpga netlists. So these are 8 different host designs. We have 6 MIT CEP, the MIT Common Evaluation Platform, as well as 2 of the largest ISCAST89 sequential benchmarks. And there's the link for you to download. So the format is again in a Verilog netlist, but we use Xilinx 7 series FPGA. So that's currently the only device we have. So we have the corresponding simulation library that's provided. And now for FPGA benchmarks in particular, the most interesting Trojans are a combination of denial of service simply because of what is available at the FPGA level. So we have 2 main types. We have this malicious LUT, which is almost akin to your ASIC level, adding additional gates. But then we have dark silicon, which is specific to the Fpga abstraction. And we also have timing aware and non-timing aware variants, which I'll get into. So here's just to show you. So again, because FPGAs are made up of these basic lookup table elements, we have 3 different types of Trojans that we can insert. The first one, again, is your traditional adding an additional gate. So here we see the LUT usage went from 4 to 5 in the top left figure by adding this extra 5-input LUT. But FPGAs have this, what we call FPGA dark silicon. So if I have an LUT, so if I look at this middle figure, this LUT6, I have an LUT2 that's mapped to it, but I have 4 other unused inputs. But from the perspective of the FPGA, that LUT is used. So this underutilized space, this extra 4 inputs are considered dark silicon. So we take advantage of that in 2 ways. One is monolithic, where we only hijack 1 LUT to implement the Trojan. Or we can cascade multiple underutilized LUTs to form a distributed dark silicon Trojan. And this only applies for higher or the newer FPGA technologies, which utilize dual output LUTs. So in that way, we're able to insert this Trojan without, perturbing the original functionality. So we'll go ahead with now a video for the structure of the benchmarks that are currently available. So here we have, this is one of the DES benchmarks. We have normal, additional malicious LUT, and then we have timing aware variant, and then we have the dark silicon, and then the timing aware. So we'll go ahead and we'll first look at the additional malicious LUT. Again, we have the same structure. We provide the lib that you need. And then we'll go ahead and we'll look at the README, which gives you details about what is available. So in this case, we have 30 FPGA benchmarks that are additional malicious LUT, and then we have 10 3-trigger, 10 4-trigger, 10 5-trigger. So because what we advertise is we have timing aware and we have essentially 0 footprint Trojans, we also provide an example script that you can use to extract the overheads just to, verify yourselves that these Trojans have little to no footprint. So we'll go ahead and look at some of the benchmarks. Again, each benchmark is provided with a corresponding log file. So we'll go ahead and we'll look at the log file. So this one is very similar to the structure of TRIT ASIC. And as we can see, this is a 3-trigger Trojan. And so in addition to, we have one new label, which is this max logic levels, because we have this timing aware. So now we see whether or not the Trojan perturbed the critical logic depth or any of the logic levels. And then we also, again, see if we provide the Trojan body. And then just to highlight the level of structural diversity we get, we'll just go ahead and look at another LUT and see this one is has different effect on the output and different structure entirely. So now we will go ahead and look at the timing aware. So what the timing aware does is it makes sure not to perturb the critical path or create a new critical path with the Trojan. So these Trojans were verified to not have any effect on the timing. And again, you can use the example tickle script there to calculate these values. So we'll go ahead and we'll look at again, the log file just to show that now when we look at the particular component about the logic level, we see that we maintain it. So again, we have the typical screen, but now I see we maintained the logic depth. So now we will go ahead and just show that even so with the timing where we can have a multi-level Trojan, and even with the multi-level Trojan, again, we didn't affect the the maximum logic depth, and we didn't affect the critical path. So now the more interesting Trojans for FPGA, which are the dark silicon, we'll go ahead and we'll take a look at that. So here for the README, I want to highlight the fact that, so we have 23 trigger, 24 trigger, but then 10 5 trigger. So we split it half and half with the monolithic and distributed dark silicon. But however, for 5 trigger, to have a monolithic dark silicon, you need a lot of LUT1s, which are not very common. So we just completely avoided that because those are few and far between. So there we only have 10 distributed dark silicon for the 5 input Trojans. So we will go ahead and look at now some of the log files. So again, same structure. So now here what we show is that now when we have dark silicon, we show what the original LUT was, the original type. In this case, it was 3 input, what it was modified to, and then the initialization value. So now here, because it was not timing aware, it perturbed the critical path and created a new longest path. So now we will show the distributed variant, what that log file looks like. So now here it just will essentially show the cascading LUTs that were hijacked, and as you can see, it became an LUT6 dual output. So again, we need that dual output for the cascading effect. And then again, because it's not timing aware, it had some measurable effect on the timing. So, and an interesting thing to note is that these Trojans have no impact on the area because we're just reusing already used LUTs. So now to get 0 area and 0 timing, we have timing aware dark silicon Trojans. So these Trojans effectively have zero footprint. So we go ahead and we look at one of the 4 trigger, just to show. So this is the monolithic. There's only one hijacked LUT. So here we show, again, no measurable impact on the logic levels. And then a more interesting case would be the cascading, which has multi-logic level implementation of the Trojan. And even then, there we have no measurable impact. So that concludes the FPGA and what's available and what you can expect if you download these benchmarks. And so I just want to give a summary. So we have Trojan benchmarks uploaded for 2 different levels of abstraction. We have Asic level Trojans over 2800. We have Pcb benchmarks. We have 150 of those. And then for FPGA, our newest work, we have over 1300 with the dark silicon and the timing aware. So with that, I will take any questions.
Hey, thank you, John. That's again an excellent presentation about all these types of Trojan benchmarks. I believe there are total 3000 benchmarks available right now for download and use in any research activities. So feel free to do that. But right now we have a few minutes for Q&A. So if you have a question, feel free to write it down using the Q&A tab of the Zoom portal. Yeah, one thing I would like to mention here is that there have been questions on the need for having so many benchmarks. As I mentioned, there are 3,000 total. If you look at each class of Trojan benchmarks, we are trying to have more than 1,000. So there have been questions on why you need so many Trojan benchmarks, right? The one important requirement of having so many Trojan benchmarks is that now, if you are trying to do machine learning based Trojan detection, develop machine learning based Trojan detection techniques, you need to have a good training set, right? Now this will enable you to do that, and this is also good for estimating Trojan coverage, right? Anytime you need to have a large data set about Trojan properties, having a large number of Trojan benchmarks would enable you to do that. So that's the reason to have so many benchmarks. So we got a question. Jonathan, why don't you take that question and answer?
Yeah, so I see. It says, how is the capability of the Trojan triggered verified? Is it merely connection to the primary inputs? No, so we use internal nets. We tend to avoid primary inputs. And the way we verify, so on each of the pages, we explain how we verify. For Asic and for Fpga, we use any justification tool or a model checking tool to essentially verify that the triggers can achieve their rare values simultaneously and through the primary inputs. And then for PCB, the way we do it is we do spice simulation, and then we find the least occurring pattern of the particular nets, and then we select that for the trigger condition.
Okay, thanks, John. Any other question? Yeah, a few more minutes left. Okay, if nothing else, we can conclude this session. But before we do, I would like Dr. Jean, who is one of the co-organizers of this session, to say a few words. Dr. Jean?
Hey, thanks, Rup. So I would like to take this opportunity to thank everyone for attending this webinar. And as Rup mentioned, we have been hosting a series of webinars in the last 2 years. And I guess Rup will introduce more of our plan for the next year. So we are very glad to have so many researchers supporting us. And we also are very happy to see that many young researchers, especially those young faculty members, send us thank you email for kind of like providing them such a great educational or research opportunities. So we also would like to encourage the attendees and all your colleagues also to voluntarily to join this webinar and to present your work. I would say thank you.
Thank you, Ian. Just a few more points before we part. Number one is that we would like to acknowledge all the support from IEEE CEDA administrative staff, in particular Amanda Osborne, Maddie Wilson, and Bailey campaign. So really appreciate your wonderful support as always. That's number one I want to mention. Number two is that the video recording for this webinar will be available soon in the IEEE CEDA website. So if you want to revisit the demo and presentation, you can do it at a later time. You can also point to the videos to your peers or colleagues, feel free to do that. And there are other videos available for the past webinars and panels and trainings. So feel free to look into the website. In terms of the next year's activities, we will continue doing these webinars and panels and trainings, and that will happen every quarter, once in a quarter. So you can expect 4 such events in 2023, and hopefully we'll continue doing that. But as Dr. Jean mentioned, we need your continuous support to be able to do this academic and dissemination effort. You can support in many different ways. Definitely feel free to use the materials in the web portal, but you can also upload your tool and benchmarks or metrics in that web portal. There's a very simple link to upload your materials. If you do that, we'll take care of posting it in the website. Also, feel free to take part in the webinars and the upcoming panels. If you have any idea about panel, please let us know. If you want to participate in the panel or give a demo, please also reach out to us. Our contact informations are in the website, CAT4Astronaut's website, and IEEE website. So you will not have any problem in terms of reaching out to us. So with that, thank you again for joining us. Thank you to the presenters, Nils and Jonathan. Both of them have been excellent. Thanks for your hard work in developing the materials. So with that, wish you all the best. Stay safe and well. We'll see you in the next webinar or in the panel for CAT4Astronaut's.